Alright, what's up guys? Welcome back to another video. In this video we're going to be going over problems, just example problems from section 3.1. So these are the problems that are at the end of the chapter. So remember that in this section we were dealing with permutations and combinations, and I'm going to go over, I think there's eight problems, and they're going to increase in difficulty. So, hopefully, by the time we're through with all these problems, the idea of permutations and combinations makes sense. So we're going to get into it. All right. So the first problem is, let's assume we have two dice, a pair of die. So die 1 is a standard die, right? So it's got the 6 regular 1 through 6 faces, and die 2, let's assume that this has the faces 2, 3, 4, 6, 7, and 9. Alright, so we've got die 1, which is a regular one, and die 2, which has these faces. It's still a 6-sided die, it just has these as the numbers on it. So we need to find the probability that the total number of dots from both dice is greater than or equal to 10. So if we throw both of these at the same time, what's the probability that the number of dots, when you count them up, is greater than or equal to 10? Okay, so this one's easy, but you're gonna write out a lot of stuff. So the easiest way we can find out, what that number is. Well, first, okay, how many possible combinations are there, right? Well, we have 6 faces here and 6 faces here. So 6 times 6 is 36. There are 36 possible combination of tosses, right? So I'll write that down. So there's 36 possible outcomes. Now, of those 36, how many of those outcomes have 10 or more dots when you count them up on the die? And really, we can just go one by one, seeing which combination would equal that, right? So, let's say we threw a 1 on die 1, then from die 2, the only other number we can throw that would make the outcome true would be a 9. Okay, so that's one combination, right? So 1 and 9. What's another one? We could do 2 and 9, because that's 11. That's greater than 10. Okay, so that's another one. And we would just really do this entire process to find all the possible combinations where n is greater than or equal to 10. N being 10, which is what the questions ask. Okay, so what other one? 3 and 7, that's 10, so that counts. That also means that 3 and 9 counts. Okay, 4 and 6, that's 10. So 4, 6, 4, 7, that's 11, that counts. And 4 and 9, that also counts. 5 and 6, that's 11. 5 and 7, and 5 and 9. And then 6 and 4. Now, you'll notice that we already have a 4 and 6 right here. The 4, that came from die 1, the 6 came from die 2. But this would technically be considered a different combination, because now the 4, where in this case it came from die 1, the 4 is now coming from die 2. So instead of 4, 6, we now have 6, 4. And like I said, that's a different combination, because the numbers came from different dice. So, okay, we'll write that down. 6, 4. 6, 6. Alright, 6, 7. And 6, 9. Okay, so how many possible combinations are there? There's 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 out of 36 possible combinations gave us a result that was greater than or equal to 10. So 14 over 36 simplified is 7 over 12. Nope, that's wrong. 18, sorry. 7 over 18. So that is the probability that the number of dots from both dice is greater than or equal to 10. It's 7 over 18. Perfect. All right, we'll go on to the next question. Okay. The next question says, a purse contains 3 nickels, 1 dime, and 2 quarters. 3 coins are chosen without replacement. So you're taking one, you're leaving it out. You're taking a second one, leaving it out. Taking a third one, and leaving it out. Find the probability of getting at least 35 cents. Okay, so a purse contains 3 nickels. So 1, 2, 3. 5 cents, 5 cents, and 5 cents. 1 dime, that's 10, and 2 quarters. 1, 2, 25, and 25. Okay, so if we take 3 coins out without replacement, what's the probability of getting at least 35 cents? Okay, well, first let's notice one thing. Let's say we take out, the 3 nickels. That's only 15, okay? So that can't happen. You can't take out the 3 nickels. That doesn't count. You also can't take out 2 nickels and the dime because that would only be 20 cents. So that means that in order for us to have at least 35 cents, one of the coins we take out needs to be a quarter. At least one of them needs to be a quarter. And then the other 2, they can be whatever, because obviously any other combination of the 2 coins plus that 1 quarter that we took out is going to give us 35 cents or more. Okay, so that means that, right, so we can either take out 1 quarter, that's one scenario, or we can take out both quarters, that's a second scenario. Now, before we, try and figure out what combination of quarter plus any other coins we can find, we need like a total probability. And we need to find the total probability of choosing 3 coins, or like how many total combinations we can take, and that's going to serve as like a foundation for whenever we do find that probability at the end, but you'll see what I mean. Okay, so we have 6 coins. How many possible 3 coin combinations can we do with these 6 coins? So for that we'll do 6 choose 3, and if you put this in a calculator it equals 20. So there are 20 possible combinations of choosing 3 coins from 6 total coins. Okay. All right. So, like I said, at least one of the coins that we take out needs to be a quarter. At least one of them. So, let's do that. Let's suppose that, we have a scenario here. So let's suppose that we took out 1 quarter. So 1 quarter is chosen. All right. Okay, so if we only took out 1/4, then let's pretend that one of the quarters isn't there. If we only took out 1/4, then we have 4 other coins to choose from, right? Because in this case, we're only taking out 1. So we only took out 1. That means we have 4 other coins that we can choose from. And because we're only taking out 3 coins, like total, and we already took out 1 coin, that means we have 2 coins left to take out. So this would be a 4 choose 2 calculation. So that means that 4 choose 2, and I think that's 4, that's 6, sorry. 6. Okay. Now, right, so like I said, this is the scenario where we only took out 1/4. We took out 1/4, and we're choosing from these 4 up here. So again, that's 4 choose 2, which is 6. 6 possible ways to choose 2 coins from 4 total. Okay. Now scenario 2, let's say that we took out both quarters. Right, because we said that in order to get 35 cents, at least 1 coin needs to be a quarter. So that's what we did in this scenario, but that also means it's possible to take out both quarters as well. Okay, so 2 quarters are chosen. So, okay, like, yeah, if we took out both quarters, that means we only have 1 other coin to choose from these 4. And that's a 4 choose 1 calculation, and that's just 4. And again, that's because there are 4 ways to choose 1 coin from the 4 remaining coins, right? You're either choosing that nickel, that one, or the dime. All right. Okay, now all that's left to do is we have to add up these probabilities. And so, or we add up these numbers in the form of probabilities in order to find the total probability that we're looking for. And what I mean by that is, okay, if 1/4 was chosen, then, like I said, that means that there are 6 possible ways to choose 2 coins from these 4. And we said that there were a total of 20 possible combinations of choosing 3 coins from all 6. So this is going to be our denominator. Okay, so for scenario 1, that would give us a 6 out of 20 probability from choosing 1/4. Now, we actually have to add this 6 over 20 again. This probability is the probability of us choosing 1/4. Let's say we chose this quarter right here. This is the quarter that we chose for this scenario. But we also have to realize that there is a second quarter that could have been chosen, right? So that's what I mean by we have to add this probability a second time, because scenario 1, we either chose this quarter or we could have chosen this second quarter. So that's why we add a second 6 over 20, right? This comes from quarter 1, which we'll just call that one, and this comes from quarter 2, which let's say is this one. So scenario 2 has 2 possible outcomes, you could say. We either chose this quarter to do the calculation for, or we chose this quarter to do the calculation for. Either way, we're only choosing 1/4. And that's why we add it twice. We have to consider both both possibilities where we either chose this quarter or we chose that quarter. Okay. And then we can add this result, this 4 over 20, right? Because, you know, if we're choosing both quarters and we only have one other coin here to choose from, again, 4 choose 1 is 4, which is over 20, and 20, like I said, is our possible, all of our total outcomes of choosing 3 coins from 6. And then we just add this up. So that's 12, so that's 16 over 20, or 4 over 5. And this is the probability of us reaching into a purse, grabbing 3 coins without replacement, and getting at least 35 cents. Alright. I hope I didn't use too many words to try to explain, but that is how we would solve this one. Alright, let's go to the next one. Alright, so we have 2 people, A and B. So A and B draw coins in turn without replacement from a bag that has 3 dimes and 4 nickels. A draws first. It is known that A drew the first time. Okay, so yeah, A draws first. Okay. Find the probability that it is known that A drew the first time. I think I missed a word. I think I missed a word here. Oh, okay. That A drew the first dime, not time. Okay. Let me fix that. Okay. So again, A draws first. It is known that A drew the first dime. Find the probability that A drew it on the first draw. Okay, so we have 2 people, right? We have A and we have B, and they're reaching into a purse, right? And they're drawing coins out. Okay, so we're told that A draws first, right? And A also drew the first dime that came out when they were drawing. Alright? Now, okay, how many did we say there were? So there's 3 dimes and 4 nickels. Okay, so in the purse we have 3 dimes and 4 nickels. Okay. A drew the first dime. A draws first, and A drew the first dime to come out. Okay, so now we have to find the probability that they did it on their first draw. Okay. Well, in order to do that, what we need to also do is we need to find the probability of them not only drawing it on the first draw, but let's say, for example, on the first draw they drew a nickel, and then B drew a nickel, and then on the third draw they drew the first dime. And we have to do that, we have to find that probability as well. So it either happened on their first draw, or it happened on the first draw, it happened on the third, or it happened on the fifth. Or I think the 7th. Let me see. No. It only happened on the first, the third, or the 5th draw. Okay. So we'll just we'll start with we'll start by saying, like, let's say that it did happen on the first draw. Let's say first draw, A goes first, boom, dime. Then that would be a 3/7 probability of that happening, right? Because there's 3 dimes over 7 total coins. So if it happened on the first draw, then that is a 3/7 probability. Okay. Here, let me actually, before I do that, I'll go ahead and say that this is actually a conditional probability problem as well. Because we're solving for the probability that A draws the first dime given A draws dime on first draw. Oh, no, that's not that. A draws dime on first draw. Given that A draws first. Right? So we're given the fact that A draws first. That's why that's on this side of the straight line. And we need to find the probability that A draws the dime on the first draw, given A draws first. All right? Now, A draws first dime. Sorry. Okay, now we're complete. Now this is what we're trying to solve for. Okay, yes, because it is known that A drew the first dime, so A draws the first dime. We know that, we're given that. And now we're trying to solve this conditional probability. A draws dime on the first draw, given that A draws the first dime. Okay. So, okay, now I'll start writing down some probabilities. Okay, so the probability that A draws the first dime on the first draw is 3/7. First draw is 3/7. Okay. Now, in order to find this probability, what we need to do is actually find this first. Our given. I mean, we're given that they drew the first dime, but I'm talking about the total probability of A drawing the first dime. So if A drew on their first draw, like I said, it's a 3/7 probability of that happening. But what about if on their first draw they drew a nickel, and then B drew a nickel, and then on A's second draw they drew a dime? So, yeah, in order to find this, in order to find the probability of A drawing the first dime, that is equal to the probability, excuse me, that A draws first dime on first draw plus the probability that A draws the first dime on their second draw plus the probability that A draws the first dime on their third draw. Right. So that's how we would find only this section. And like I said, that comes from the fact that, you know, either they draw it on the first, they draw a dime on their first draw, or, like I said, they grabbed a nickel, boom, dime, or they grabbed a nickel, then B grabbed a nickel, then A grabbed a second nickel, then B grabbed their second nickel. Okay, that's all 4 nickels gone. Now A draws a dime. Okay, so we already have this probability, which is a 3/7. And now what we have to do is find these next, you know, whether it happened on the second or the third draws. All right, so in order to do that, we're going to sort of like be eliminating coins from the purse. And what I mean by that is this. Okay, so let's say that it happened on A's second draw, right? They drew a dime on their second draw. That means that if they drew, so yeah, they must have drawn a nickel for it to happen on the second draw. So that means that first they grabbed a nickel, okay? That is a 4/7 probability of them grabbing a nickel on the first draw. And I'll label this A's first draw. All right. Now, B, it's B's turn to grab. They also grabbed a nickel in this situation. So A grabbed the first nickel. Now B grabs their first nickel. There's 3 left, so it's 3/6, right? 3 because it's 3 because A grabbed the first nickel, and it's 6 because A grabbed a coin and didn't replace it. They just took it out. So this is B's first draw. And then, actually, we're not adding, we're multiplying. Okay. Now it's A's turn again. And if they're drawing a dime on their second draw, that means there are 3 dimes left, but there are 5 total coins left. So this would be 3/5. And this is 6/35. And this is A's second draw. All right. So again, A's first draw, they grabbed the nickel. That's a 4/7 probability of that happening. B's first draw, they also grabbed a nickel. That's a 3/6 probability of that happening. 3 nickels left and 6 total coins left. A's second draw, well, they finally grabbed the dime. So that's times 3/5. There's 3 dimes left, and there's 5 total coins left. You multiply it, and it's 6/35. All right. So we have this, and we have this. Now we need to find the probability that A draws the first dime on their third draw. Okay. So third draw. So it's pretty much like this. It's going to be pretty much this process right here, where A's first draw, they grabbed a nickel instead, so that's 4/7. And then B grabs a nickel, so that's 3/6. And then A grabs another nickel, so that's 2/5. And then B grabs the last nickel, so that's 1/4. And then finally, A grabs their first dime, the first dime to be pulled. So that's just 3 over 3, that's just 1. And that is equal to 1 over 35. Okay. Now finally we have so finally we have A drawing a dime on their first or their second or their third draw. So we finally found this probability. A draws the first dime. But what we're interested in is this conditional probability. Okay. Now, if you remember from the conditional probability chapter, just the formula for conditional probability, right? It's the probability of A given B is equal to the probability of A intersect B over the probability of B. Right? So, we want to find this, and we already have this probability of B. So this is half of the equation. So the probability of A given B is equal to something over, and we add up these probabilities. Yes, we add up these probabilities, and this gives us 22 over 35. So that goes down here. 22 over 35. Okay. What about this probability? A intersect B. Well, that's the same as saying A draws dime on the first draw and A draws the first dime. Or rather, A draws the dime on the first draw. Well, we found that earlier. That was 3 over 7. So, yeah, in which situation does A draw the dime on the first draw and A draws the first dime? Well, that only happens if A draws the dime on the first draw. So yeah, that's 3 over 7. And that goes here. This is our A intersect B, the 3 over 7. And that goes on top. And this is equal to 15 over 22. And that's our answer. It's 15 over 22. And that is the probability that A draws the dime on the first draw. Okay. Now we'll go on to the next one. Okay. So we have 3 people here. We have X, Y, and Z. They roll a die until someone rolls an even number. Find the probability that X wins. So find the probability that X is the one that rolls the first even number. Okay. So since X is the first to throw, so they're throwing in that order. They're throwing X first, then Y, then Z. So like that. So since X is the first to throw, in order for X to win, they have to throw an even number on the first, the fourth, the 7th, the 10th, and then you go by threes, the 13th, the 16th, because that's their turn. Their turn is the first turn, or the 4th, or the 7th, anyway. So the probability that the first even number occurs on the nth throw is And it actually looks like this. Okay, so yeah. So X throws on the first, the fourth, the seventh, the 10th, and then whatever. Okay. So the probability that the first even number occurs on the nth throw is this one. This problem is a little more maybe not as maybe abstract, I guess, because here I'll show you guys why. It's 1 over 2 n minus 1 times 1 over 2 is equal to 1 over 2 to the n. Okay. What does this mean? This part right here, which includes the n minus 1, this represents all the throws that have been odd up to this point. And because n minus 1 represents the odds. Let me go back to this. Well, the reason it's 1/2 is because half of the faces are even, right? But if I go back to the textbook, okay, the probability that the first even number occurs on the nth throw is, yes, okay. This is true since it requires n minus 1 odd throws followed by an even throw. Okay, yeah, okay, so right, so 1/2 again represents the fact that half of the faces on a standard die are even. So you have a 1/2 probability of throwing an even number when you throw a die. This n minus 1, like I said, represents all of the past throws that have been odd. So, you throw it once, oh, you get a 1. You throw it a second time, oh, it's a 3. You throw it again, it's another 3. So they're all odd. This 1/2 right here represents the winning throw. Right. So what we're doing is we're multiplying basically all of the odd throws that we've thrown times the winning throw that finally wins, and that gives us this. And the reason we have an n here is because we don't know exactly when we're gonna throw the even throw. Like, this game could go on, I guess, forever technically. So that's why we're using instead of a real number here, we're using just the n. N representing this winning throw. And like I said, this represents all throws that have been odd. So yeah, we're multiplying, like I said, all of these odd throws that we've thrown times the winning throw, which gives us this. Okay. Now, and actually, okay. Okay, I won't write that, but the probability that the first even throw occurs on throw n, right? We got that. okay, so like I said, n represents the winning throw. Okay, let me backtrack a little bit. I'm still right in saying that we don't know when it's going to happen, but n represents like that throw that it could happen on. So like yeah, we would just replace this n with like 1, or we would replace the n with 4, or we would replace the n with the 7, because that's when x throws, and that's who the question is asking. Well, when would x win? When would x throw the winning throw? And yeah, that's basically what this is. So like I said, that n we could replace with the 1 or with a 4, with a 7, with a 10, until, you know, forever. So that means that the probability that x wins on first or fourth or 7th row is equal to 1/2, and well, there's kind of an understood 1 right there. Okay, one thing, let me see. Let me make this a little bigger. So again, it's 1/2 plus 1/2, and then the n would get replaced with a 4, plus 1/2, that n would get replaced with a 7th, plus, and like I said, this realistically could go on forever. You know, x could win on the 1st, the 4th, the 7th, the 10th, whatever, like for a while. So there's no like real stopping point. But if we were to add up all of these numbers, you know, eventually, of course, it's more likely that it'll happen on the first throw. It's a little less likely it's going to happen on the 4th. It's even less likely that it'll happen on the 7th. So this denominator is just going to keep getting bigger and bigger and bigger. And that 1 is just going to stay the same. And it's like the difference in probabilities is just going to get so much bigger, and that this 1 is going to be over like the million or like the 10 million, and that is just such a very small fraction. It's very insignificant. It's very unlikely. But what this boils down to is, and we're just going to get like an approximation answer, it's actually 4/7. That's the answer to this probability. So like I said, this question didn't have like a very, I guess, concrete way of solving it, or very like, you know, like where we could see it happen like the last problem. It's just more of like a, I guess, yeah, just like a little more abstract, more just, you know, abstract, I guess. I can't really think of another word to describe it. But yeah, ultimately, like I said, these fractions are just going to get so much more smaller that what we end up doing is just approximating that it will be a 4/7 probability. So this question, maybe not the best, or maybe I might just be not explaining it very well. Like, hopefully, I guess maybe the important thing is you guys understand this part, and that I understand it, right? These are all the throws that have been odd up to this point. We multiply it by the winning throw, and that gives us this fraction right here. And this is the fraction that we use to find the probabilities of x winning on the 1st, the 4th, the 7th, the 10th, which we replace the n here whenever we add the fractions up, right? 1 over 2 to the 1, 1 over 2 to the 4, 1 over 2 to the 7, so that the answer to this probability is just an approximation. And I mean, you could keep adding, 1 over 2 to the 10 or 1 over 2 to the 13. You just keep going if you wanted to. But like I said, at some point, you're going to be adding like decimals. So there's not a real concrete answer. It's just, like I said, it's an approximation. So, but that's how you would do this one. We'll go on to the next one. These next ones are more like we can actually see these and like, I don't know, like tangible, I guess. Okay. So, it's another urn question. Okay. Urn 1 contains 7 red and 3 black balls. Urn 2 contains 4 red and 5 black balls. A ball is selected randomly and placed from urn 1 to urn 2. Then, 2 balls are randomly drawn from urn 2 without replacement. Find the probability that both balls drawn are red. Okay. Okay. Let's see, how do I want to start this? Well, okay. Let's just start with the fact that okay, let's start with the first thing that happens, right? So we have that a ball is selected randomly and placed from urn 1 to urn 2. Okay, there are 2 possibilities. Either the ball was red or the ball was black. So we'll write that down. So R1, we'll say R1 is the ball placed from urn 1 to urn 2 is red. Okay? And like I said, the other possibility is that it was black. So we'll say that's B1. So the ball placed from urn 1 to urn 2 is black. Okay, so that's the first thing that happens in this question. The second thing that happens is that 2 balls are randomly okay. So a ball is selected to place from urn 2. Then 2 balls are randomly drawn from urn 2 without replacement. Find the probability that both balls drawn are red. Okay. So, like I said, this is the first thing that happens where we go from 1 to 2. And now what we're doing is we're taking 2 balls out of urn 2 without replacement. We're taking them, putting them out, taking a second one, putting it out. And we have to find the probability that both balls that we took out are red. Okay, so this is, we'll call this next scenario R2 and say that the 2 balls drawn after the transfer are red. Okay. Okay, now, let's see. Okay, so ultimately we're just trying to find this probability right here, the probability of R2. Okay. But what is this equal to? What formula can we use in order to solve for this? Let's consider another thing. If we're only transferring 1 ball from urn 1 to urn 2, but we have to consider both of these possibilities, what we can say is that these 2 things, they can't happen at the same time, right? either the ball that was transferred was red from 1 to 2 or it was black. That makes them mutually exclusive, right? Because they can't happen at the same time. It's either one or it's the other. Okay. So, So what that means, okay, so, right, either one happens or the other happens. Okay. Or, that's union. And we'll just kind of write that to the side, right? Either R1 happens or B1 happens. Okay. But R2 has to happen in conjunction with either one of these, right? So they both have to happen at the same time. So that would be an intersection. Okay, so we have to find the intersection of R2 happening if R1 happens, and the intersection of R2 happening and B1 happening. What does that look like? That looks like this. So the probability of R2 is equal to the probability of R2 intersect, and then in parentheses, R B1 or R1. Hopefully you guys can see that. Because right, that first transfer happens, and we also take 2 balls out. So both things happen in this question, so that's an intersection. And like I said, either R1 happens or B1 happens, so that's a union. And that's what we have written right here. And I guess we can separate this out a little more. So we are finding the probability of R2 intersect R1 plus the probability of R2 intersect B1. Okay. And how do we find intersections? Well, we've already seen this a million times already. We can use conditional probability to do that. And what do I mean by that? I mean, like, we can rewrite this out even more, right? So this would look like the probability of R2 given R1 times the probability of R1, and that's this right here, plus the probability of R2 given B1 times the probability of B1, and that's that right there. Okay, so now we have conditional, so we have been able to basically find what we need to solve for in order to find the total probability of R2. So again, we rewrote this in this form where we realized that either B1 or R1 has to happen in conjunction with R2. That's why there's an intersection there. And then we just separated this up a little more to have 2 probabilities added with each other, the intersection of R2 and R1 plus the intersection of R2 and B1, and then we rewrote these intersections in the forms of conditional probabilities. And this just comes from the conditional probability equation, where, you know, R2 over R1, or like the probability of A given B is equal to the probability of A intersect B over the probability of B, but rewritten so that instead of solving for the conditional probability, we're solving for the intersection. And that's what we have here. This is 1/2 and this is the second half. Okay. Now what do we do? Well, how do we solve for this? How do we solve for these conditional probabilities? You know, and we do that by let me see, how do I want to start explaining this? Well, I'll start by saying this. We can actually solve for PR1 and PB1. So in the question, earn 1, I'll write it over here. Earn 1 has 7 red and 3 black. 7 R and 3 black. Okay. So what's the probability of R1? What's the probability that a ball placed from earn 1 to earn 2 is red? Well, earn 1 has 7 red. So that means that is a 7 over 10 probability. So I'll write it kind of right here. So the probability of R1 is 7 over 10. And what's the probability of B1? Well, the ball placed from 1 to 2 is black. There are 3 black balls in earn 1, so that's a 3 over 10 probability. All right. Okay. Now for these conditional probabilities, these are going to be a little, well, we'll see. Okay. And I might need this too. Okay. Maybe not. Okay. So we're given that a ball placed from 1 to 2 is red. So let me write down earn 2 over here as well. Earn 2 has 4 red and 5 black. Okay. If we place a red ball from 1 to 2, that means we now have, instead of 4 red balls in earn 2, we now have 5. All right? And then let's say that the 2 balls drawn after the transfer are red. Well, if we're drawing 2 red balls from 5 total, that is a 5 choose 2 probability. 5 choose 2. Okay. And this is just looking at the red balls. But we have to look at the total probability of choosing 2 balls from the entire urn, right? There are now 10 total balls in urn 2 after we've transferred 1. And if we're grabbing 2, then that's 10 choose 2. Okay, let me try and re-explain maybe. So we transferred 1 ball from earn 1 to earn 2, and we're saying that it was red. That gave us 5 red balls in earn 2 now. That gives us 10 total balls in earn 2. This 10 choose 2 came from the fact that there are 10 total balls and we're choosing 2, right? We're pulling 2 out of earn 2. This 5 choose 2 is only taking into account the red balls because that's what we're grabbing. Here we're grabbing 2 out of 5 red balls, but here we're grabbing 2 out of 10 total balls. So in order to find the probability of so in order to find this conditional probability, we would need to find the probability of us grabbing 2 red balls from 5 red balls over us grabbing 2 balls from 10 total balls. Okay. Now we're going to do the same thing over here. R2 given B1. Alright? So, we're back to normal over here. So yeah, let's say that they transferred a black ball over. So now we have 6 black balls instead of 5. But we're still choosing 2 red balls. Well, now we have 4 red balls to choose from. So in this numerator, we would have 4 choose 2. Over, 4 choose 2 over 10 to choose 2. This is a 10. And again, we're grabbing 2 red balls from 4 total red balls over us grabbing 2 balls just in general over from 10 total balls. Okay. Hopefully that made sense. Because, right, we have to consider us grabbing from just one specific group of things over us grabbing from the entire set. And that's how we would find these conditional probabilities, this one and that one. And like I said, this is just the probability of R1, the ball placed from 1 to 2 is red, right? Because there's 7 red out of 10 total balls, 7 over 10, versus us grabbing a black ball, putting it from 1 to 2, which is 3 over 10. There's 3 black, 10 total balls, and yeah. And like I said, these are these conditional probabilities. And you just put all this in your calculator and you get 44 over 225. And that's our answer. That is the probability of R2. So we have to consider like more scenarios, I guess. You just can't get lost in like, you know, all of the total possible outcomes for these kinds of questions. You have to consider every scenario, every possibility, and that's what we did here. Okay, we'll go to the next one. Calculator has a random number generator button that can display a digit from 0 to 9. If we press it 4 times, what's the probability we get a 0, a 5, and 2 9s in any order? Alright? So we're trying to get a 0, a 5, and 2 9s in any order if we press this calculator button 4 times. Okay, first let's look at the total possible number of 4-digit pairings, because that's going to serve as our numerator for this question. The numerator for the final probability that we want. Okay. So the total possible of 4-digit pairings, that would just be, oh, and look at that, actually. This is like the, so we have types here, right? We have a 9 which shows up twice, so that's one type of element. We have a 5 and we have a 0. So in total we have 3 different types of like things or elements, whatever you want to call them. So we can use the equation from earlier, from the last video, for finding probability using types, which is this one. It's n factorial over n1 factorial times n2 factorial times nt factorial. Okay, so remember on top we have the total number of like things that we're looking for, or just things in the set. So in this case there's 4, because there's a 0, a 5, and 2 9s, 4. So 4 factorial over how many items are in type 1? 0. Well, there's just one. It's just 1 0, 1 factorial. How many items are in the second type? There's just 1 5. So that's just another 1 factorial. There are 2 9s that we want in our answer. So that would be times 2 factorial for this last bit. And this is equal to 12. Okay, I kind of got ahead of myself. I said we were going to find the total, like, possible pairings. But let me backtrack and say that in order to find the total possible pairings, all we would do is do 10 to the 4. And that's 10,000. Okay. These are the total possible 4-digit pairings, just like in total. 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, all the way 0, 0, 0, 0, all the way to 9, 9, 9, 9, right? Everything in between. There are 10,000 possible 4-digit pairings. 10 to the 4. 10 because there are 10 digits 0 through 9. 4 because that's how many numbers we want in our, in our answer, or how many numbers we want in our ordering, I guess. So this is the big number. This is the big number that I was trying to look for, but I got ahead of myself. And instead I went ahead and I found how many possible ways we can rearrange these 4 numbers. So in this case, the answer to the question would be 12 over 10,000. So again, 10,000 is the total number of 4-digit orderings we can have. And 12 is the total number of orderings we can have with only these 4 numbers up here. And I used that using the types formula, or the formula using the types right here, which we found out to be 12. So it's 12 over 10,000. That's the answer. Okay, sorry, I got ahead of myself. Okay, next question. All right, this is a 2-parter. Okay. Okay. In Canada's 649 lottery, 6 numbers are chosen from 1 through 49 with no repeats. A ticket costs $10. If you match 3 numbers, you win $10. Okay, find the probability of matching all 6 numbers. Okay, this one's easier to do. So, one ticket has 6 numbers. And the numbers go from 1 to 49. Alright. So what's the probability that we match all 6? This one's easy. If we have 49 total numbers, then we only have to choose 6 to match. 49, choose 6. And that's basically it. It's just 49 choose 6. Which is equal to 13,983,816, or rather 1 over that, right? This is how many total. This is how many total possible 6-digit combinations using the numbers 1 through 49 we can have, but only one of them is the winner. So 1 over that. So that's the probability of winning this lottery. Okay. Now this actually has a second part to it, because in the question it said, if we match 3 numbers, we get $10. So now we have to find the probability of winning $10. So that means we only have to match 3 numbers on our ticket. Okay. So let's see. How do I want to explain this one now? Okay. Let me see. How do I want to start explaining this? 6 choose 3. 20 ways of choosing 3 numbers. Okay, so there are 6 choose 3, which is equal to 20 ways of choosing 3 numbers from the 6 on our ticket. Okay, now let's see, 6 choose 3 equals 20. Okay, what this is telling us, or what this represents, is that there are 20 ways of choosing 3 winning numbers on our ticket from the 6 total numbers on our ticket. Okay. Trying to see if there's a better way of explaining this. Okay, maybe we'll start in another way. Okay, so in order to win $10, we know that only 3 numbers have to match, right? And one ticket has 6 numbers on it. Now, let's suppose that our ticket looks like this. suppose our ticket has the numbers 1, 2, 3, 4, 5, and 6. But the winning ticket has the numbers 4, 5, 6, 7, 8, and 9. Okay. So our ticket matches 3 numbers on the winning ticket, right? And these other 3 numbers don't. So, because there are 49 total numbers to choose from, and 3 of the numbers we chose are winners, then 49 minus 3 is 46. Okay? But, like I said, these 3 numbers cannot match the remaining 3 numbers on this ticket. So, really what we're doing is we're taking out 6 total numbers from the 49 that are presented to us. So, like I said, 3 of our numbers match with the winning ticket. Okay, that means that we have 46 numbers left to choose from for these 3. But actually, no, it's 43 numbers that we have to choose from, because these numbers can't match these. And so, and you know, there's also no repeats. So, you know, this winning ticket used up 6 numbers, okay. We matched 3. These 3 can't match these other 3. So, and they can't match any of, you know, these 3 can't match any of these numbers, and there's no repeats. That means that these 3 we have to choose from 49 minus 6, which is 43 numbers. Okay. So 43 choose 3 is equal to 12,341. Okay? And that is only, these are the total ways, or the total combinations of finding 3 non-winning numbers. Okay, but what about finding 3 winning numbers? Well, that would only be 6 choose 3, because if we have a ticket that has 6 numbers, but we're only choosing 3 to win, that would be 20. Right? So, from our ticket that has 6 numbers, we're only choosing 3 numbers to be winners. There are 20 ways to do that. And for the remaining 3 non-winning numbers, we have to choose from 43. Because, you know, 3 numbers are winners, 3 numbers are non-winners, but they can't be any of the numbers that are in the winning ticket. So it's like saying this winning ticket ate up 6 numbers already. That's why from the 43 numbers that the winning ticket did not eat up, 3 of them have to be non-winners, non-winning numbers. And there's 12,341 ways to do that. Okay. hopefully that made sense. Maybe I'm struggling explaining this a little bit, but I hope so far it's made sense. Okay, so now we have these two, combinations, numbers representing combinations. Now what we would do is multiply them, because we're trying to find how many ways can we have a winning ticket that only has 3 winning numbers. So 12,341 times 20 is 246,820. 246,820. These are the total possible ways of us having a winning ticket that only has 3 winning numbers. Okay? Or, excuse me. There are 246,820 ways where a winning ticket matches 3 of our numbers. So now what's the probability that our ticket matches 3 numbers on a winning ticket? This would be over the 13 million that we found earlier. 13,983,816, which is equal to 0.01765. Okay. Language matters a lot. The way you ask and word these things matters a lot. Because what this number is this is how many ways a winning ticket matches 3 of our numbers. But we need to find the probability of our ticket being a winning ticket that has 3 winning numbers. So we would put that over how many possible number combinations there are for a ticket that has 6 numbers, which gives us this, and this is our answer. Okay, hopefully this one made sense as well. This one was a little hard to maybe explain, but I hope it made sense. Okay, last question. And this involves a deck of cards. Okay. A full house in poker consists of 3 cards of one rank and 2 of another. So for example, 3 kings and 2 fives, or 3 queens, 2 aces, whatever. If you're dealt 5 cards at random, find the probability you were dealt a full house. Okay, so a full house looks like this. So we have 1, 2, 3, 4, and 5 cards. So 3 are 1 rank, and that's like the ace, 2, 3, 4s, whatever. So like an example would be a king and a king, another king, another king, and 2 aces. What is going on? I don't know what's happening. There's dogs working outside. Okay. This is just an example of a full house, right? And I mean, this could be like hearts, this could be diamonds, this could be spades. Ooh, that looks not good. Okay, maybe, what's the other one? Clubs. And then, you know, the ace of diamonds and the ace of hearts. Okay, so that's just an example of a full house. Okay, so what's our big giant denominator that we need to be able to find this? That is just the total, like, possible hands that can be dealt, right? How many possible 5 card hands can be dealt from a standard deck of cards? Well, if there's 52 cards in a total deck, and we're only choosing 5, that's 52 choose 5. So 52 choose 5 is equal to 2,598,960 total 5 card hands that can be dealt. Okay. This number is very important to us. We'll have to keep this in our thoughts and prayers. Okay. Now another thing to consider is that there are 13 ranks from ace to king. So, right, there's the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. 13 ranks. Okay? In a full house, we have a pair of the same rank. So how many possible pairs from 13 ranks can we find? So that would be 13 choose 2, right? That's 78 pairs of ranks. Right? I hope you guys can still see that. It's getting dark. Okay. So, yeah, there's 78 pairs of ranks. So, you know, you have the, like here, you have the ace of diamonds, you have the ace of hearts, or the ace of diamonds, the ace of spades, the 2 of hearts, the 2 of diamonds, like that. Excuse me. No. Okay, okay. There's 13 to choose 2, which is equal to 78 pairs of ranks in one suit. In one suit. Okay, so no, it's not like this. What this means is that if you have one suit, and suits are the diamonds, the hearts, the clubs, and the spades, you can pair up the ace of spades with the 2 of spades, or the ace of spades with the 3 of spades, the ace of spades with the 4 of spades, like that. That is what this means. I forgot to add this one suit. Okay. So, okay, that's what this means. Okay. Now, each rank has 4 cards coming from 4 suits. So each rank has 4 cards from 4 different suits. Like, you have 4 different kinds of kings, right? 4 different kinds of queens. Okay? That means that there are 4 choose 3, which is equal to 4 ways of choosing 3 cards of the same rank from 4 cards in that rank. I'm going to write that out. There are 4 ways of choosing 3 cards of the same rank from 4 cards in that rank. Okay, so there are 4 ways of choosing 3 cards of the same rank from 4 cards in that rank. if you have the 4 kings in front of you, there are 4 ways of choosing 3 of those, right? You know, you take the king of hearts, clubs, and spades, or you take the king of hearts, diamonds, and spades, or whatever. If you have the 4 kings laid out, there are 4 ways to only take 3 of them. Okay? And there are 4 choose 2, which is 6 ways of choosing 2 cards of the same rank from 4 cards of that rank. Okay, so this is basically the same thing as this, except now instead of choosing 3 cards, we're choosing 2. So again, if you have the 4 kings laid out in front of you, there are 6 ways of choosing 2 of them. You know, in any combination, there's 6 ways of doing that. If you're only choosing 2. Alright? Now that we have this and this, we can multiply these together. 6 times 4 is equal to 24. And that is equal to the total combinations consisting of 3 cards of the first rank and 2 cards of the second rank. Let me write that out. 24 combinations consisting of 3 cards of the first rank and 2 cards of the second rank. All right. So if you have, okay, so there's 24 combinations consisting of 3 cards of the first rank and 2 cards of the second rank. So if you have the kings and the queens in front of you, then, you know, you choose any of the 3 kings and 2 of the 3 queens. That's 1 full house. But there are 24 different ways to do that. What I mean by that is, if you take the king of spades, the king of clubs, and the king of diamonds, and then after that you take the queen of hearts and the queen of diamonds, that's 1 combination. Or you keep the 3 kings that you chose, and then you took the queen of hearts and the queen of clubs, that's a 2nd combination. That's what this is saying. If we multiply these 2 numbers, that's how there's our 24 total combinations of choosing 3 cards of the first rank and 2 cards of the second rank. And we also have to consider, well, what if we take 2 cards of the first rank and 3 of the second? So instead of taking 3 up here and 2 down here, what if we take 2 up here and 3 down here? And it's the same. There's also 24 ways to do that. So 24 combinations of 2 cards of the first rank and 3 cards of the second rank. I'm writing down. So we have to consider that as well. There are, you know, that's like the other possibility is that, yeah, you take 3 up here, 2 down here, or you either take 2 up here and 3 down here. Okay. What this means is if we add these two 24s together, then that means that there are 48 possible full house hands using only 2 ranks, right? Because in this entire example, I've been talking about kings and queens. Okay, what about the other ranks? What about the aces, the twos, the threes, the jacks? This is only the total possible combinations using 2 ranks, but what about all 13 ranks? Well, what we would do then is multiply 48 by 78, right? Because there are 78 pairs of ranks. So, yeah, so one pair of ranks is the king and the queens. Another one is the kings and the aces, or the kings and the jacks, or the kings and the tens. So, because there are 48 possible full house combinations using 2 ranks, but there are 78 total pairs of ranks, then we would multiply 48 times 78, and that gives us 48 times 78 is equal to 3,744. Oops. 3,744 possible distinct full house combinations. All right. But what we want to know is what's the probability that we get dealt a full house? Well, we have the total number of distinct full houses. We would just put this over this 2 million number that we found, which is the total number of 5 card hands that can be dealt. And I'm going to write it up here. So I'm just going to write it right here. So that's 37,444 over 2,598,960. And that is equal to 0.00144,058. And that is our answer. So just to preface, or just to, not preface, but just to go over this kind of quickly. First, we find how many total 5 card hands we can be dealt. Then we found how many possible pairs of ranks in one suit there are, right? So if you take only the diamonds, you can pair up an ace and a 2, an ace and a 3, a 2 and a 3, a 2 and a 4, like that. 78 pairs of ranks in one suit. Then we found how many ways there were of choosing 3 cards of the same rank if we had all 4 in front of us. Then we found how many ways we can choose 2 cards of a different rank if we had all 4 in front of us. Then we multiplied these 2 numbers, and that let us know how many combinations we could make if we choose 3 cards of one rank and 2 of the other. We also said that there were the same amount of combinations if we chose 2 of that first rank and 3 of the second, which gave us 44. But that only tells us that there are 40, or that gives us 48, but that only tells us that there are 48 possible full house hands using 2 ranks, right? But in total, there are 13. And we would multiply this 48 by 78. Because there are 78 pairs of ranks. There are 78 pairs of ranks times the 48 possible full house hands using only 2 ranks. So 48 times 78. And that gave us 3,744. And we put this number over the entire total 5 card hands that can be dealt. And that gives us this. Hooey. Let me see something. Okay. Ooh. All right. Hopefully this one also made sense. Let me see. Let me see something. Okay. Yeah, I'm done with this. So, dang, almost 2 hours. Okay, hopefully, like I said, this one also made sense. I'm gonna go over like 13 problems myself and try to explain them in the next video. But I'm gonna go get some food first. So, that's the end of this video. Hopefully it made sense.